I see some sort of nodding faces. Yes, thank you. So yeah, welcome everybody to this introduction to higher order networks. And as I said before, but also to keep this on record, right? So there's some required readings before sort of seeing this presentation in this kind of flipped classroom format. So I'm not going to repeat everything that's in the required readings. Rather, I'll sort of give a sort of selective overview of a few things that I think are interesting and worthwhile noting, and assuming that most of the things that are sort of in there in terms of definitions and so on, you're familiar with, but you know, basically interrupt me at any point in time if this is not true. Nonetheless, we're of course going to start with some bigger picture here, with some higher order motivation, right? So basically, higher order networks, this is the topic of this training network, right? And why are we interested in this, right? And I personally really like sort of this overview news article by Austin Benson, who unfortunately left academia, but he had been working for some time on higher order networks as well, right? And then like me, sort of coming from the side of network analysis and complex systems, basically over the last 5 years or so, I would say there has been an influx of new data and of new methods, right? And so there has been a realization basically that if you want to study complex systems, be it neuroscience, neurological systems, whether it's social networks or ecological systems, technological systems, what have you, right? There are many times interactions that you're going to miss if you just use a classical, let's call it classical here, right? A network abstraction or a graph abstraction, right? And the rationale is basically to say, let's say, okay, if we have a graph, then basically we have a set of vertices and we have a set of edges, right? And by definition, the edges are pairwise relations between the nodes, right? So it's me talking to Agnes, for instance, and Agnes talking to Chris as the course coordinator. But the three of us talking jointly together about the research training network, for instance, right? This is not captured by a relation that defines the data, right? And so that's why, of course, people have moved on, right? And they've looked into variations of models for this higher order data. And I would say sort of in some sense, the most straightforward and flexible is to replace a graph by a hypergraph. Because what is a hypergraph? I mean, if you have a graph, right? This is just the set of vertices and edges. And now what we're gonna do, and here important, right? The set of edges is basically a subset of the relations. Well, okay, how do I say this? Okay, let's say it's a subset of A, B such that A, B element vertices, right? So what I want to say here, these are tuples. They are pairs, basically pairwise relations, right? And if you go for hypergraph, it's basically the same, but what you're gonna do is you're gonna eliminate this restriction here that you just have pairwise relations. So you're allowing for any sort of relations, right? P-adic relations rather than binary. So dyadic is the sort of, or binary is the word for pairwise, right? And then p-adic or multi-adic or polyadic, what have you, right? There are many words saying the same thing. We have basically relations between multiple entities. Now, there are other models that come into play as well. If you are looking at higher order networks, you can, of course, think of a graph in terms of its associated abstraction, in terms of its sort of representation as a matrix, right? I mean, a matrix is not the same as a graph, but a matrix is a great way to store the information that you have in a graph in a algebraic way, right? So at first, a matrix, right? This let's say an adjacency matrix that you derive for a graph is nothing but a table that encodes, let's say, this edge structure, right? But then why do I say a matrix is not the same as a graph, right? A matrix also defines a mapping from some input space to an output space. And if it's a graph, and if you're looking at an adjacency matrix, then it's basically a mapping from the vertices to the vertices, right? And by basically looking at this mapping, and for instance, using tools from linear algebra, such as the spectral theorem, we can actually now reveal some properties of this matrix, of this mapping, and that translates back to properties of the graph. And that's really the cool thing, right? So that's why representations, matrix representations, actually matter, right, for graph analysis and for many other reasons, right? Because we can actually do computations with matrices in very different ways than if you just had, this sort of just two sets, right? One of vertices and one of edges, right? So representation matter, and I'll dwell on this a little bit further. But of course, if you say, okay, now matrices and graphs, there's a close relations, right? Then you might say, okay, if we go higher in the tensor, so a matrix is a basically tensor of order 2, right? It's 2 dimensions. Then you can also think of, okay, why not represent hypergraphs by tensors, right? And of course, people have done this, and then you go into tensor methods, tensor algebra, multilinear algebra, right? And you can exploit these methods. I think this is, in some sense, less common. Most people still prefer to work with matrices and encode the structure of these hypergraphs with matrices, which had, it's just, let's say there's more tools out there to work with those matrices rather than tensors. Tensors are a bit more complex, right? And then, of course, there is, let's say, another big player, and these are like simplicial complexes and more general cellular complexes. And one way to think about simplicial complexes, and I'll actually will say that this is maybe not the most fruitful way, but it's certainly conceptually a very, very simple way to say this, is that a simplicial complex is nothing but a hypergraph where you require all the subsets of a hyperedge to be edges in the hypergraph as well. So you could think about this as like it's a simplicial hypergraph. What does it mean? If I have a 5-way relation, then I'll have all the subsets of 4-way relations in there as well. I have all the subsets of the 3-way relations. All of them have to be in there. And if this is the case, then I call this object a simplicial complex, right? And maybe you think, oh, this is a natural relation, because after all, if I know Chris and Chris knows Agnes, and we 3 know each other, we also know each other pairwise. So in some sense, from a modeling, sort of from a conceptual point of view, this can be a natural relation. Sometimes it's also not a natural relation. If you think of, for instance, I don't know, like chemical reactions, right? You might have a reaction that requires 3 ingredients to be in place to, get a new product, let's say, and precisely if only 2 are in place, nothing's going to happen, right? So this is an example where this kind of modeling assumption breaks down. But
Sorry, we had a question in the chat in the meantime.
Okay, so there you go. This is the first instance where I've missed the question in the chat. Thanks for.
So the question is, how do you encode a higher order interaction with a matrix and not a tensor?
Good. This is a good question, and actually we're gonna get to this in a second. I will talk about this. You need multiple matrices, of course. There are actually multiple ways of doing this. But bear with me maybe a couple of more minutes, and I'll talk about this. And if there's still a question, then of course, jump in with your question again. What I will not talk about today, although this is interesting, and by all means, if you're interested in this, ask questions about this as well, is you can also think about a higher order networks in terms of motifs, right? So let's say you think about connectivities between certain, let's say, I don't know, like triangles, right? So how well are 2 triangles connected? How well are any kind of motif, where motif is just a certain a subgraph that you're interested in. Maybe it's a clique, or maybe it is an open triangle, some sort of wedge or what have you, right? So there you can also be interested in how this higher order patterns are distributed in your network, how they are connected, what can you learn from them, right? And the other thing that sort of is lumped together here in this picture, like tensor and higher order Markov chains. So higher order Markov chains, I'll not talk about because they bring sort of another aspect in there that's related to temporality and dynamical processes on networks. We can talk about it maybe quickly in the context of dynamics on higher order networks, but I'll not focus on this too much. Again, here the connection you can kind of see by sort of attaching yet another object to a graph. So very often people analyze graphs by basically looking at the associated Markov chain to the graph. And what does it mean is basically you look at a graph, you look at the network, right? And then you basically identify each node with a state of a Markov chain, right? So basically this is a state, you can be here, you can be here, you can be here, right? And then you look at the transitions between the states in terms of, let's say, a random walk, and then you get a Markov chain, right? So you have a random walk on this network. And now by analyzing the random walk, again, you can say something about the network, right? So this is where yet associating the graph with yet another model, let's say, makes sense. Now, if you want to go to higher order Markov chains, I mean, the Markov chain is basically really there's sort of a one-to-one mapping, if you want, from the Markov chain and its state transition graph, which is really like a graph as this that you can represent by a network, and its transitions is then the weighted adjacency matrix. And on the other hand, you have the graph, which is just this network. Right? And so Markov chain means where I go, if I sit here, does not depend on where I have been before. This is the Markov property. But let's say if you have trajectories over space, it might matter whether I arrived, let's say, at this node, whether I came from here, maybe I ended up here. And then maybe when I come from here, I always go there, right? And so this could not be modeled as a Markov chain, and therefore this simple graph abstraction doesn't work. However, what works actually is if you let's say lift this, so basically if you include more states, if you create another network that is not the network of the vertices in this case, but in this case it would be the network of the edges, then actually you can represent, let's say, second order Markov chain, and you can expand it. So in some sense, the higher order Markov chains, by going to a large enough state space or a larger enough state space, you will always have a network representation. And that's why I don't want to talk about this here, not because it's uninteresting, but it's sort of conceptually it goes into a slightly different direction. Okay, so this was motivation for why has there been this explosion of higher order network analysis, higher order network method development, and so on, interest in research in this. And as you can already see by all those kind of terms that I've thrown at you in the first 5 minutes now, there are actually a lot of different perspectives that get compounded if we're talking about networks and higher order networks. And indeed, this is actually already the case if we're talking about networks, right? So networks we all love because, you know, they're like these higher order networks, they appear almost everywhere: biology, technological analysis, social networks, right? But what I want to argue here now is that even though everybody, at least everybody in this call for sure, is interested in these networks, what people actually are interested in terms of, let's say, scientific questions, in terms of how they use these networks, how you think about network models, is somewhat different, right? So the modeling paradigms, if you want, that underlie this they're different, and that means that people have different questions in mind and also different kind of methods. And sometimes there is a confusion because people talk about, let's say, different, the same object, but they have different questions in mind, and therefore then the debate about like, oh, you know, you should really use this or you should really use that. But let me make this maybe a bit more precise, right? So now sticking first with a graph network content, no higher order relations here, right? So I would say that maybe this model paradigm that I call networks to model relational data is perhaps the oldest one in this sort of complex networks literature. So at least this is, I think, that sparked a lot of interest initially with works by Strogatz and Small World, and you know the scale-free networks and so on. And basically, what people did is that they monitored relations, right? So in the Small World case, it was relations between routers on the internet, for instance, or in other contexts, right? And the idea is that the data that you have at hand, that you sort of observe, that's the object of your scientific inquiry. These are relations between entities, right? So we have a graph, right? And the vertices, these entities are fixed. They are not sort of, you know, you have them. These are define the scope of your system. But what you want to measure or what you want to analyze is really the connections. And at a higher level, pun not intended, the rationale is that there has been some process, whatever it was a human design or it was a stochastic process, that basically, you know, created those links between those entities. And by understanding how the links, how the edges are structured, we can learn something about the system. We can learn maybe about that process even, right? And so that's why we want to analyze this relational data. And so one example is, for instance, that you observe relations between people in a social network and you want to find communities. I mean, this is a whole topic on its own, right? Like how you're going to do this and how is a community even defined. But conceptually, I hope you can see what I mean with this, right? You want to find a pattern in this data where now the edges are the units of measurement. They are the thing you're interested in, right? Or, for instance, you have a food web. Again, I mean, how do you get a food web, right? It doesn't exist in the wild. You don't go into the forest and you suddenly see links between animals. No, what you do is actually you observe links, right? Actually, not you probably, but some other people that invest a lot of time, ecologists, they observe, you know, what animals, I don't know, hunt each other and so on, right? Predator-prey relationships is the example that I picked here, right? And now you have this network, right? And the measurements were the edges, and you want to look at the bigger system and say, okay, maybe there is a key species here that is really, really important for this, and you can see this by looking at this network structure, right? So what I want to argue here is that certainly one type of questions has to do with analyzing, let's say, the edge set, analyzing the relations between entities. And the goal here is somehow that you want to analyze, model, and understand these connectivity patterns, right? And this typically has to do then with methods from, you know, statistics. You're trying to model these relations and so on. Machine learning comes into play, many things, but the perspective that I want to emphasize is that the data is the network itself, right? So it's the topology, if you want. Now, how do you gonna lift this concept now to a higher order? This is relatively easy to say, right? Like basically before we were talking about relational data, and the only relations we said are those that count, right? Are the pairwise relations. Or in other words, what we actually did is if we saw a relation of that kind ABC, right? If you ever saw, let's say again, me and Agnes and Chris talking, you would have said, oh, you know, this is a social network. This is a triangle. They all have pairwise interactions. This is what you would have modeled if you're going pairwise, right? And then you can basically, you know, put a statistical model, put a probabilistic model over this, and you can say, okay, maybe how likely was this to occur, right? This kind of phenomenon, the triangle. However, if you want to go beyond that, right, there's a priori Of course, there are computational restrictions, but a priori, there's no reason why you should split this into pairwise relations, right? And you can basically, of course, set up a model that has triplet relations, that has quadruplet relations in there, and you can try to keep this, right? I mean, a priori, no reason in terms of from the modeling perspective that you might not want to do this. In fact, you could always argue that the more information I keep, the better, right? There is, of course, a price to pay that typically if you have not enough data, and I mean, higher order data is easier, it's not easier to come by, it's actually more difficult to come by, right? Then fitting those models is going to be more complicated, and fitting those higher order models is also going to be computationally more expensive. But, you know, let's leave this aside and say, okay, now this was models in terms of relational data, right? What is there out in the wild as well? Is there something else? And of course there is. And okay, this should look like a nice looking S manifold here, but let's not dwell on this here. Okay, so let's say model paradigm 2. This is now, if you're coming from the world of manifold learning and topological data analysis, and I don't know, many other areas, right? In this world, typically you don't really start with a graph a priori, but very often you just start with some point cloud data from which you can construct a graph. And actually, let me go to the next slide. Okay, here I have a nicer plot. I will just loop back in a second. So let's look on the left side here of this picture, right? So if you have a huge data set, you've measured something, it's very complex. What you want is to understand this data, of course, in a much more simplified manner, right? And an assumption that's very often made is that rather than this data, let's say this is maybe gene expression, so you have like a 20,000 dimensional space or something like this, right? You assume, or actually you hope, that this data lives in a much lower dimensional space. However, that space is not a linear vector space, but it's actually nonlinear in the sense it's curved. It could be, for instance, a manifold, right? So something like this here, like a sphere, right? So basically all the data points live on the sphere. But a priori, you don't know this. So how can you extract this? And there's a very rich literature on basically extracting this kind of information from data. And one way, and the simplest way in some sense, is to say, okay, let's draw around each of these points a little epsilon ball. So you pick some distance and you say, if 2 points are close by, I connect them with an edge. So identify each point with a vertex and I connect them with an edge. Then I'll get a graph, right? And now I can basically analyze this graph to get some type of dimensionality reduction. So the idea is that in this huge space here, in this bigger space, right, the distances, the Euclidean distances that you can measure, they are pretty much meaningless because this is such a vast dimensional space, and distances in high dimension, in particular Euclidean distance in high dimension, doesn't really work well. So what you want is to pick out the local, the short, distances basically. And what you effectively do is you're saying, okay, this point and this point, how close are they? Well, I have to probably walk through the whole graph here. So in some sense, you replace the distances in the original space by the distance that you find in this graph. And this way you can unroll that space, right? So this is an example from ISOMAP. This is from the 2000s, a paper. And this idea, I think, is sort of a really powerful idea. In some sense, what you're going to do, basically, you have a complicated object. You think of this complex object as a discrete sampling from an underlying manifold, from an underlying space. You construct a discrete version of this or proxy of this, you analyze this, and you get this back. And indeed, this is one, another perspective, if you want, on how when people use higher order networks, basically very often you start with point cloud data. Sometimes you also start with a graph. The graph typically comes from some sort of geometric origin, however, and then you have tools to basically understand this graph. And by doing this, you say something about the point cloud or the underlying object. Now you can translate this to higher order if you basically, rather than having a single epsilon ball and creating a graph, well, what you're going to do is you actually now, and this is topological data analysis, this is basically persistent homology, you have an epsilon ball that you keep growing, right? And then you look at how does the graph change, and not actually do you look at how does the graph change, but you construct a simplicial complex or another complex from this by a so-called frustration. So initially, if you have epsilon equal to 0, right, nothing will be connected, so the graph is completely disconnected, nothing interesting happens. Then you keep going, and at some point you create edges, and then you have a rule that says, for instance, the rule could tell you like, okay, as soon as I have a triangle, I fill it, and I call it a 2 simplex, right? The filled triangle. And I keep going with this. And what can I do now? I can now basically use tools from algebraic topology, and those tools basically keep track of the number of connected components and the corresponding quantities that you can define that are associated to higher order. So the first is a number of connected components, basically, that's what you keep track of. The second is the number of holes that you have in the space. Then it's like the number of 2-dimensional voids and so on and so forth, right? So you've probably all seen this at some point, but if not, we can talk in the Q&A about this particular construction as well. So model paradigm C is basically now, again, different thing. If you're interested in dynamical systems on graphs, right, then very often the name of the game is as follows. You start with some predefined local interaction rule that comes in the form of an ordinary differential equation or some other update rule. And then you want to run this on a graph. And you're asking yourself, how does the graph, how does the underlying network influence the emergent behavior that you can get from your dynamics? So things like synchronization, how does the network have to be structured for let's say, for a motor oscillator or whatever, like a consensus process to converge to some kind of interesting point, right? So how do we get synchronization? Do we get consensus? Do we get, I don't know, let's say in an ecological systems, do we get animals to die out? How does the network structure influence this, right? And so now here, it's important to note that unlike in the first sort of modeling paradigm, where the edges were really the random entities that you wanted to analyze, in some sense, what you're saying here is that the network is arbitrary, right? So you want to analyze this for all possible networks, but it's fixed, right? It's not typically modeled as, oh, there may or may not be a relation between, a fox and a rabbit. You typically assume that, yes, foxes hunt rabbits, right? And this you keep fixed. You might be interested in another world where, rabbits hunt foxes, and you can play that game within this framework. But again, it's not a random variable, these edges, right? Again, typically. So now the name of the game is basically you start with a local interaction model and with some topology, and you want to understand the long-term dynamics. If you want to play this game in a more, let's say, machine learning way, then rather than having dynamical systems, so data associated to the nodes that evolves over time, you might have feature data that's associated to the nodes, right? So it could be attributes. This could be, for instance, like me being based in Aachen, having a certain, length, a certain age, or whatever. All these feature attributes I have as a vector that's attached to me as a node. And now I want to predict, however, let's say feature attributes of other nodes in the network. Then again, it's sort of like you have some information about the vertices or features, rather features that are associated to the vertices, and you want to exploit the network structure to, let's say, make predictions about certain other nodes. And now in contrast to the dynamics, where sort of the interaction rules, the update rules about how do I update my my state, my feature vector, is given a priori. In the machine learning or signal processing context, really you have a desired outcome. You want to predict, you want to estimate certain things. And in some sense, your goal is to design an update rule such that it actually does the right prediction. And so this is a different flavor, but I mean, I like to think of those things combined at least. So, well, what have I said? Basically now the name of the game is that you want to leverage this interplay between structure and data supported on that structure to understand the observed system, right? And how can you go a higher order with this? Well, I think this is relatively simple. Now, if you allow higher order entities to be present, right? You can basically have update rules that account for triplets, that account for whatever. And the interesting thing here, however, is that coordinate changes matter. And I'll get to this later. So now this is just like this to give you sort of the high order overview, right? And I think, I mean, at least for me, it helps to categorize this into these 3 boxes. This is not the only way in which you can do this. And in fact, this is in some sense, this is a lie, right? Because in the reality, none of this is like really mutually exclusive. You can have variations and combinations of all this. Nonetheless, I think in terms of mathematical tools, in terms of where people publish, and in terms of how to identify the computational problems in there, for me, it helps to do this, right? And again, feel free to use this differently, but I'll go with this. So now this is a very lengthy intro, but I think this one was one of the main points that I wanted to hammer home. Higher order networks are not higher order networks. It really depends. You can model the same system in 3 different ways and might get 3 different answers, and yet they're all correct because the question you're asking is a different one. So let's look quickly at this, what I wanted today say. I mean, basic concepts, I've already dwelt on this. I will now do this a little bit furthermore in terms of representations. I want to quickly now touch about all of these 3 perspectives and give you some hints and some pointers, and then we'll be done, right? I mean, so it's not so much time in this hour, but we can continue in the questions. This thing you've probably read, right? What are higher order networks? And the intro in particular should have felt familiar to you if you have read this. There's a huge review by Federico Battiston and others, and Giovanni is also included, who's part of the ITN, that contains, you know, lots of things, lots of applications. There is a nice review about, again, representations, which is the topic I'm mostly focusing on today, by Leo Torres and others, including Tina Eliassi-Rudd. There are many, many more out there, so this is just a selection. Stefano Boccaletti has something about dynamics and hypergraphs that is interesting to read. Yeah, many things. So let me again say something about basic concepts and misconceptions. And now I'm going to talk about these representations, and also the matrices will appear. So I've alluded to this in the beginning already. So I mean, if you have data about interactions, right, then if you want to break this down into pairwise relations, right, and you basically say the basic unit of interaction that there is a pairwise interaction, then you can aggregate this and you can get you'll get a graph, right? Note that you not always start with data about interactions, right? I mean, sometimes you actually start with a network and a dynamics on top of it. So you're not sort of breaking this down in some way, right? Like, for instance, a street network is not something of that kind generally, right? Now, the interesting thing is, if you have a graph, right, so you can now, of course, play your usual game. You can try to analyze, I don't know, network motives. You can do community detection. You can maybe look at this in terms of how do you have groupings. In fact, I'll mention this briefly. Every graph has a bipartite relation, not just bipartite graphs, but every graph has a bipartite representation when it comes to a data structure of how to present this. But now we are here, right? And this is this picture that I think is most prevalent in literature, but basically says that, okay, if you have a simplicial complex, right, then the nice thing is you can basically have 3 dyads. You can now distinguish this from a 2-simplex, from a ternary relationship, right? And if you put this together and you have this sort of subset inclusion principle, meaning that the triplet implies that the tuples, the 2 tuples, right, and so on, everything down, you call this a simplicial complex. And if you don't, you call this a hypergraph, right? Okay, fair enough. Now let's look at the data structures for the simplicial complexes, and let me tell you about why I'm not so fond of thinking about simplicial complexes just the form of hypergraphs. And the main reason is that if you wanted to think about simplicial complexes as a form of hypergraph, I mean, okay, then maybe the facet representation is all that you need, in the sense that, yes, keep track of the subset inclusion property, but all you need is somehow to say that the nodes A, B, C, you know, they have a ternary relation, maybe they have also a binary relation and so on. But this representation here, right, where these are the vertices here, and these are your relation, covers everything, because basically by knowing that you will have the subset inclusion, you can recover the fact that in the simplicial complex, there has to be something, there is an edge, right? There is a BC as well. This gets a little bit lost here. It's not lost in this nicer, I would argue, nicer representation. It's called the Hasse diagram, right? And I'm not sure whether somebody wants to be in the recording or not, but at least I can hear something else. But I assume this was not a question. So the Hasse diagram is another representation of the simplicial complex, and I think it's more informative in the following sense. You start here with the vertices, right? I'll call this vertices or 0 simplex. Then you have the edges, and then you have the 2 vertices on the top. And what I think is really crucial here, that it shows you that what is a 2-simplex? A 2-simplex, yes, you can think about it as a triplet interaction, and you think about it in terms of hypergraph. But really, a 2-simplex is a relation between 3 edges. Okay? So if you look at this map here, this is basically telling you what is the boundary of this triangle. The boundary of the triangle is 3 edges. It's not really that the boundary of the triangle is 3 nodes. No, this is not really what this sort of algebraic topology construct encodes, right? And if you use a representation of this like this, this is a little bit lost. In fact, in the literature, I think this is sometimes getting a bit conflated, right? So really, what is an edge? An edge is a binary relation, right, between 2 vertices. What is a 2-simplex? A 2-simplex is a relation between 3 edges, right? And so, of course, you can conveniently write this in this notation, because, you know, this is like much quicker than say, okay, what is this? This is basically AB and CA and BA, and put this into a tuple. You can collapse information that's redundant, but what you will need if you want to do, let's say, algebraic topology type calculation, you'll actually need that information. The boundary of a 2-simplex is not somehow like 3 nodes and 3 edges. No, it's 3 edges, right? And that's why I think this is in some sense a more useful way to think about it, right? Of course, the other thing is fine if you just want to think in terms of hypergraphs with additional subset inclusion properties, right? So now here do we come to the way of how to represent these things in the matrix. And there's many, many ways in which you can represent this in terms of a matrix. And I have, you know, like a priori, there's no preferred way. I have my preferences, let's say, and I'll tell you why I prefer to think about certain things like this, but it doesn't mean that the other things are not relevant, right? So one thing is to think about is in terms of an incidence matrix, right? So an incidence matrix is basically, if you go in here, it's a matrix encoding of this bipartite representation, right? So you have on one side, you have the vertices, and on the other, you have the relations. And you put an entry here, and how you encode this exactly is yet another thing. I'm not going to talk about it. Typically, you just put a 1 in there, just an indicator, right? And they say, okay, nodes A, B, and C, they are part of this triplet. So I put a 1 here, right? Maybe. And then nodes B and C are part of this pairwise relation, and that's why I put a 1 and B and C, right? So this is an incidence matrix. Now you can do the same with the simplicial complex. It's done here. By the way, these figures are taken from Federico Battistan's review. Again, highly recommended to read this. In fact, you should have read some parts of this for this. This is now sort of doing the same encoding with the simplicial complex. And you will see that there are more relations here appearing. Why? Because everything that's implied by ABC has to be encoded in the simplicial complex, right? So this, however, right, now in some sense, this representation conflates this picture, right? So it basically suggests, if we now think about this matrix as a mapping, it suggests that there is a, let's say, a direct path going up here, right? Which you may or may not want to have. If you want to think about, again, algebraic topology and these kind of relationships, this is probably not the representation you want to choose. Now here are other representations. The intersection profile, which is basically saying like, okay, how do now relations, so in some sense you could think about this as a line graph, if you know what this is in the graph world, right? So this would be the line graph in the graph world if we had just did a network. So the intersection profile basically says, okay, A triplet ABC, how does it overlap? It overlaps with BC, it overlaps with CD, at least in the in the vertex C and so on. And now you can put numbers in there, maybe in terms of how much it does overlap and whatnot. Right? Similar story here. You can, of course, also encode this now in terms of an adjacency, right? And so the adjacency now, here is just, you have the vertices. So in the intersection profile, you look at basically how are the relations coupled to each other. And in the adjacency world, you look at how are the vertices coupled to each other. And you may want to account for certain relations to be stronger if you have, let's say, a triplet relation, right? But you can see if you just use this, right, you'll lose information, right? And this is maybe not what you want. I mean, of course, you can work with multiple representations. There are other ways of accounting this. So in some sense here, we either looked at the relations or the matrix representation that shows how the relations interact with each other, right? So this is the A, B, C's and so on, how are they coupled, or how the vertices are coupled, and the mixture, like the incidence type of coupling. But you can also, of course, keep track of the different dimensions, right? And so now notice that here, right? Now I say, okay, this is the incidence matrix of the 3 edges or 3 hyperedges, right? And there's just a 1 3 hyperedge, so I only have this vector here. It's an incidence vector. And now I have a matrix that encodes the 2 hyperedges, right? And notice that in the simplicial complex world, right, I would now say this, I would not call it incidence matrix if it's me, right? So because in incidence matrix in the simplicial complex world, we'll typically say that, AB, how is AB coupled to ABC? How is BC coupled to ABC? And how is CA coupled to ABC? And then this here should not, this is a typo if you want, right? So in a hypergraph, you can split edges by cardinality, but basically an edge is a relation between vertices, right? In the simplicial complex, or more general in the cellular complex, a higher order, a 2 simplex, a K simplex, you don't have to think about this necessarily as a simplicial hypergraph if you want, but if you want to do algebraic topology, think about it as a relation between low order relations. This is more sensible. In particular, then you can actually analyze these mappings because they basically tell you like how to go from a boundary to a higher order object, or vice versa from a higher order object to its boundaries, right? And by analyzing this maps, this is really the essence that is in topological data analysis. So now we talked about tensors briefly, right? I can basically create a a tensor representation from this as well. So how do I going to do this? I mean, basically, let's say I'm going up to have up to 3 order relations, so between 3 type of nodes, right? Then I will need to encode that, you know, A, B, and C, they are part of a triplet edge. So I want to, for instance, put this here into an adjacency tensor, right? And so a tensor is nothing but a stacking of matrices, right? Why is this sometimes a bit cumbersome? Well, basically, you would need one tensor for each type of cardinality, right? So this is the two-way. If you have a graph, right, and you have just binary relations, so you just need a tensor of order 2. That's the matrix, right? Because basically you need to say like, okay, A can be related to any A up to whatever F, if this is the largest vertex of your graph, right? But if you have triplet relations, you need a tensor of order 3. If you have quadruplet relations, you need a tensor of order 4. So in principle, you need to have a stack of tensors, a matrix, then a tensor of order 3, and so on, to keep track of all of these relations. So tensors, therefore, often appear in the context of let's say, uniform graphs in the sense that you have only relations that are k-ary, right? And then you can work with a single tensor, and then it's nice. If you have heterogeneous relations, tensor representations can be somewhat problematic, but it is what it is. Okay, so now here's the thing. I warned you at the beginning that a matrix is not a graph, right? But there is a tendency to say, like, you know, I mean, I have a matrix. So matrix, I can associate a graph with, right? So isn't everything just a graph? Like, why are we doing all this shenanigans with higher order, right? In particular, if I have a graph, right? Now here's the promised bipartite representation. I could always think about the graph in this incidence representation where I have vertices and I have edges, right? This is nothing but the incidence matrix representation of the graph. Now mapped as a graph here, right, for convenience. Now here I have a hypergraph, which is also a bipartite graph, if you want, right? So I have vertices and I have their relations. And here I have now this is slightly more general than a simplicial complex. It's a cell complex where I now allow other facets to be present compared to just triangles, right? So, but again, I'll have the relation that everything that's a boundary of this, in this case, for instance, is a cube, has to be part of the cube, has to be part of the cell complex, and then everything that's a boundary of every edge has to be present. So you'll have all the vertices, you have all the edges, and you have these two cells. But look, this looks like a graph as well, right? So aren't we just doing graphs, right? And the answer is no, right? The answer is no. I mean, conceptually, you can, of course, always say, oh, there is a matrix. That means there is some sort of other graph in which I can understand this. But the moral here really is that these are all representations, matrix representations or graph representation of something that's in the real world. In the real world, there is no graph typically. There is no hypergraph. There's also no cell complex. These are also abstractions, right? And now how I encode these abstractions in terms of, let's say, data structures, right? This is yet another different thing, right? So matrices, for instance, right? I can encode, if it's a sparse matrix, with a list. So like basically it's a list where I say, okay, I only encode the non-zero entries. In the computer, sometimes there's just this list stored, right? And this allows it to do matrix operations fast, for instance, in the sparse matrix sense, right? It does not mean that every matrix is a list, right? So these are just two representations of a different thing. And in particular, representations can make sense because they they make tools available, mathematical tools that you might want to use. Matrix representations are particularly useful because we have a spectral theory for matrices. We have lots of cool numerical linear algebra. We can do, you know, many good computations with this. This is really why you should drive to getting a matrix representation. It's not that the matrix is somehow the universal object of the world or what have you, right? Like by no means. But it is useful because we can do, we have a lot of theory and we can put it into the computer in an easy way, right? So don't get sort of tangled up in this, even though, yes, I can describe most things by a graph. They're not graphs. So now I have about 5 minutes or something. That's maybe 10 minutes left to really quickly go through this. And I just wanted to show you a bit more examples, because now actually, if you've understood this, then it's fine, right? So now, high order relation data. How are we going to go about this? So my take on this is actually a relatively easy one here. I don't want to tell you a lot about a lot of different models and so on, but okay, what do I need to get basically models for high order relational data? I need to define a probability distribution over the space of possible hypergraphs that I allow, right? And now one way to do is basically pick your favorite representation that you have, and maybe this is a matrix representation, right? So maybe this is a matrix representation, and you have here the vertices, and here you have hyperedges, right? And now, if I tell you, let's say, okay, I have, I don't know, capital N vertices, and I have capital M hyperedges, right? I can generate lots and lots of different models by basically assigning probabilities in whatever way to this array, right? To this matrix. This is basically using the bipartite representation and therefore the matrix representation in this sense to generate a model for a hypergraph, right? So you basically use one representation to generate a model for something in the other world. Many models for hypergraphs go down that route, okay? And you can go through the literature. I think it would be a useful exercise. I'm not sure anybody has ever done this, but basically, you can look at every of these representations that you have here and see how they are used in terms of models for hypergraphs. Another variant would be maybe you like K regular hypergraphs, so only hypergraphs was just with K-arid relations. Well, then a tensor model could be nice, right? And so you can basically say, okay, I have a model, a tensor model. I put certain probabilities here. If I don't want to span this entire cube, what's typically done is you do a decomposition of this tensor into rank 1 tensors, for instance, right? So you assign basically, why this is not synchronizing, okay? You assign numbers. You have basically a vector of numbers, and then you expand the whole tensor as a product of these 3 numbers, right? This would be one way to do it. There are many others. There are lots of models in the literature as well that for K regular hypergraphs that follow this format. And again, you can do more, right? I mean, everything that you can do in graphs, you can now lift to the hypergraph world and play the same game. And in some sense, I think there are very interesting things that can happen, but let's say in terms of the recipe, there's not much too difficult that can happen, right? Chapter 3, again, this is going to be a very briefly, just some salient points that I don't think are maybe not that well captured in the papers that you had to read. The first thing is this relation between simplicial complexes and Hodge Laplacians and so on, right? So if you go down that road of geometry and topology of data, and you're doing your usual persistent homology thing, right? Then what you can keep track of is essentially Betti numbers, or more generally homology groups. So that is basically these holes, right? Like how many connected components do I have, how many cycles, and so on. What this doesn't tell you, however, is how close am I to being a whole and so on. Like how close is this? How do the individual components, how do the individual points relate to this whole? Right? This is something that you can actually get. However, if you don't look at this just at this persistence diagrams, but you keep track of what the associated matrices do, or in this case, the associated Hodge Laplacians, they are nothing but linear, well, or not linear, but basically they're combinations of the incidence matrices. Their spectral properties basically give you everything that you get in persistent homology as well. Why do I want to sort of emphasize this point? Not because that I don't know why this text here is so malformatted, but the idea is as follows. Let's say if you wanted to analyze a data set, you might get a 1D persistence diagram, or you get this birth-death persistence diagram, right? And then you could pick out certain features, and you could say, wow, this had, I don't know, 3 loops in it, or maybe it was 4 loops, right? And you didn't pick out one. Now, what does this really tell you about the individual points, right? So persistent homology is very useful if you want to have an outcome, let's say a feature that describes the data set as a whole. But if you want to go back in and say, how did this point relate to any whole, then it doesn't, this thing here, this doesn't tell you anything about it. So what you can do instead is basically, for instance, you can go back, look at this whole, look at the associated 0 eigenvalue of the Hodgson and basically project this onto the data. And then, you can basically get a score of how much an individual point relates to a topological feature that you've seen in the data. The reason this works is that the kernel of the Laplacian is the so-called harmonic form, let's say, the harmonic form of this space. And the harmonic form basically has a one-to-one correspondence to the properties of the topological space. Okay, 2 more minutes left. Dynamics and data on top of higher order networks. Well, if you're now giving a higher order object, right? Maybe it's a higher order hypergraph of a three-ray relation. So it's a 3 uniform hypergraph, right? And you want to say like, let's study now dynamics on this. So I'm going to look at an ODE. This is a function, right? And the function depends on my 3 neighbors. And now here's a sort of very simple observation, right? That if your function f now, right, is linear in X, so it's linear in these arguments, then there is always going to be an equivalent network dynamical systems of this form. So somehow, if you have this, right, you can always rewrite it as such if f is linear, right? And in a way, this is very trivial. You're gonna have these slides later on as well, so you can do the calculation yourself, right? Basically, everything factorizes. You just get out, let's say you have here a linear interaction function of this form. This is a consensus-like function, so something like synchronization if you want, but in linear terms, linear synchronization. You'll always get this, right? And the matrices just look different. So now, again, does this mean that this here is not a hypergraph dynamics, but it is a network dynamics? Well, who knows, right? I mean, basically, you've defined it as a dynamics on top of a hypergraph. It means that there is an equivalent representation in terms of a network. That network, however, is not the same thing as this hypergraph, right? This is an effective network. It has different weights and so on and so forth, right? But you define it, right? And whether you want to call it a hypergraph or a network, it's up to you. Maybe calling it a network would be the simpler choice in terms of like Occam's razor type of argument. You make a simpler make a simpler model, right? On the other hand, you could say, well, the network might be complicated in terms of structure. The hypergraph is just 3 regular, so maybe this has some advantages, right? So again, representations, models matter. So what we have learned in this little example here is that you need nonlinear interactions. So you can write the dynamical systems. Basically, then a network is not enough. Nonlinearity on its own is, however, also not enough. There's a little example that's also in the paper. I invite you to discuss this more in the next hour. That basically shows that, yeah, you can have nonlinear interactions, and yet your relations, they can basically factor it again into a single matrix, and therefore you can think about it as having an effective network at the back, right? Here's another thing that's maybe a bit more subtle, and it's not in the paper, is that actually turns out that any nonlinear system you can lift into an infinite state space and create a linear but infinite dimensional dynamical systems. And sometimes this is actually not infinite dimensional, but it's finite dimensional. And this technique is, is basically the Koopman operator, or change of variables, if you want, or kernel trick in machine learning. And here's an example, proof by example. This always works, but again, the operator might be infinite dimensional. So here's an example. I have this very tiny two-dimensional nonlinear system. I define a new state, and that state is x1 squared. And now I have a three-state dynamical system, and I look at the ODE associated to this, and it turns out to be linear. And now if I believe that every matrix is a network, then you can represent this as a network if you want. And so there's an effective graph dynamical system with a larger set of states that describes this dynamics exactly, right? Yet again, and I think I've making this point now for the thousandth time, I think, this does not really mean that one thing is a network dynamical system and the other is not. It is within your chosen representation, right? This would not be a typical network dynamical system, I would say, whereas within your now differently chosen representation, this could be thought of as one. In fact, you don't even need Koopman operators in this to kind of see this, right? So representations matter. If I just look at the linear dynamical system, right, of this form, and now let me say I just do a state transformation, right? So I do a state transformation in terms of the eigenvectors of my adjacency matrix. Let's just say it's an undirected graph, so this exists, everything is fine, right? So now I use new variables, yi. These are just the eigenmodes, and they are all decoupled, of course, right? This is simple linear algebra. So you have basically now a completely decoupled set of equations. The network has somehow disappeared, right? And of course, this should show you, right, that again, representation, choice of state variables, and so on matters, right? But because if this was fundamentally a network problem at the beginning, this is still in some sense a network problem. However, what you see now that these variables here actually they depend on all the nodes. So if you want to have a system that basically operates like this, that has a local distributed update, right? These updates, they cannot be computed if your real system was, let's say, a street network or whatever, and you measured things on the individual edges. You could not update your yi coordinates here, your new states, without having access to the complete network, right? So in that sense, this is still not fully decoupled because the physical variables, let's say in your space, in your system, were the x's and not the y's, right? So on the math side, we can do a lot of tricks. But if you have a physical reality that is that these are the things that you can measure, sometimes the state transformations don't help, right? And okay, so now I hope I have thrown enough controversial things at you to have an interesting discussion in the next hour. And with that, I want to stop here. Thank you.
Thank you very much for this interesting talk. Now I will stop record.